In this segment of the video, we're going to show you how we add acid to the quartz and then digest that quartz so that in the end what we have is a clear liquid that we can extract the beryllium and aluminum from. We dissolve quartz in acid because the chemistry we do to purify that quartz and to extract the beryllium and aluminum from the quartz is in liquid phase. So we've got to get the quartz into a liquid and then we can work through the extraction protocol. So the equipment setup is fairly simple for this step. We're going to start with full personal protective equipment. And that begins with wearing rubber shoes in case we were to splash acid on our feet. That includes wearing long pants in the laboratory. That includes a full yellow rubber smock that goes from your neckline down most of the way through your pant legs. Then on our hands, we have double gloves. We have a thin nitrile set covered with a much thicker nitrile set. And to protect our eyes and face when we're working with any concentrated acid, we have goggles on. In fact, we pretty much have goggles on anytime we're in the lab handling any chemistry. But in this case, we also have a face shield, which you'll notice in the videos. And that face shield is a double protection against splash from hydrofluoric acid. HF is a hazardous acid. The fluorine that's in there, the fluorine anion, is very reactive. And so if it ends up on your skin, it will soak into your skin and react with things like calcium. That can disturb a lot of your nervous system and muscle reactions, but it's also extremely painful as it complexes with the calcium. So we use full body PPE to prevent any chance of HF acid coming in contact with our eyes or our skin. So we have a beaker in which we decant the acid and we can measure the volume of acid in there. We're trying to add about 100 milliliters to each sample. That doesn't have to be exact. That's about 5 times the amount of quartz we have, and the stoichiometric ratio for dissolving quartz is a little bit over 3. So we add an excess of hydrofluoric acid to make sure that we drive the reaction to completion, which dissolves the quartz. You'll see that we have bottles. Those bottles have quartz. In the last video, you saw us add that quartz and mass the quartz in, along with specific masses of beryllium and aluminum carrier. These bottles are enclosed in a plexiglass box that's made partially of Teflon. The front and the top are plexiglass on there so we can see into the bottles. The bottom of the box is aluminum that transfers heat from the hot plate. And then the sides are Teflon to help resist degradation from the acid fumes that are in the hood. Having the samples in the box serves several purposes. It's an additional safety layer. It's a protection. The way the box is designed, the sample bottles can't tip over. But the other thing the box does is keep the heat uniform around the bottles, and that dramatically increases the speed and the uniformity of digestion. There's a hot plate, and that hot plate is externally controlled, so you'll be able to see the hot plate external controller. That controls the temperature of the hot plate to about 1 degree Celsius. It's digital, it's easy to read, it's safe. Having the controller outside the hood means that the corrosive acid fumes cannot influence the controller, and that's a whole lot safer than hot plates that are in the hood where the acid can get into those controls. We are working in specific types of fume hoods. These are polypropylene plastic fume hoods, so they're non-reactive to acid fumes. They're also clean air laminar flow hoods, which means that the air coming into the hood has been filtered when it came into the room, filtered again when it goes into the hood, and filtered one more time before it gets onto the samples with what are called ULPA filters. These are Teflon filters. So inside these fume hoods is essentially the equivalent of a class 100 clean room, and that helps us keep our blanks low. The front of the fume hood has a perforated surface and forms what's called an air curtain. So the room air comes in, dives down through the front of the hood, and the samples never see it. The fume hoods are really an integral part of our safety plan in the laboratory because they fully evacuate all the fumes that are generated during acid digestion, and they keep the workers who are working in front of them safe. We add about 100 mils of concentrated HF to each sample, and the samples are up to 22 grams of quartz. This is a process where we really concentrate. People working on it do it typically in the morning. They do it when they're fresh, and they always do it with someone else around in the lab for safety. Very important, the lid of each bottle is vented with a very small millimeter-size hole so that the bottle can never become pressurized as it heats. That lets any of the reaction gases out of that small hole and keeps the bottles from pressurizing. So after we add the acid, we initially let the sample sit for several hours or overnight, and that will let very fine-grained quartz react. It's an exothermic reaction, so as the quartz digests, it tends to get hot. After that initial settling period, we start the samples at typically 60 or 70 degrees Celsius. We leave them there for an hour or two, and then we slowly bring them up, usually in several degree to 5 degree increments over time. And when we get to about 90 degrees, we tend to slow down because in that temperature frame, the samples can react very violently as they start to heat up. So we go very carefully around the 90 to 110 degree range. And that's the temperature of the hot plate, not the temperatures of the sample necessarily. This whole process can take several days depending on how fine-grained the quartz is. We can actually see the quartz as it's dissolving and as it's giving off gas. Small particles of quartz sort of burp up from the bottom and slowly settle. Once we get the samples up to a temperature of about 135 degrees on the hot plate, we let them sit until they are completely clear with no residual material, and then usually let them sit an extra night after that to make sure they're completely dissolved. If we don't dissolve all that quartz, our final calculations are going to be incorrect. Because this digestion process takes several days, we usually have 2 batches running at a time. One batch of samples is digesting, while the other batch is going through the process that you're going to see in the rest of these videos. So we're basically layering one batch on another, so we're always ready on a Monday morning to start a new batch. So let's recap the quartz digestion process. Remember here that our goal is to have the process be done safely and the quartz to be completely dissolved by the end of the process. We use concentrated hydrofluoric acid. First, we have to wear full personal protective equipment to handle the concentrated HF. We work in a fully exhausting fume hood to do this. We safely add about 120 milliliters of HF to each sample bottle, measuring it out in a calibrated beaker. We then slowly and cautiously increase the temperature of the digestion over a period of a couple days until the quartz is completely digested. We do this in a way that does not result in a rapid reaction, and therefore no boiling over and no venting of dangerous fumes. Again, we continue this digestion until the quartz is completely and fully dissolved and the solutions in the bottles is clear. Then we cool them overnight and start the next part of the process.